So, say we want to find the reaction force at A in the y direction. We're going to split this structure into a primary structure due to the point load and a secondary structure due to the reaction force. And then for each of these structures, we're then going to draw real moment diagrams and virtual moment diagrams. Then we look in the product integral tables and we see what formulas we need to use to find the displacement at A due to P and displacement at A due to the reaction force. And then we apply compatibility condition, which says that the displacement at A due to the point load plus the displacement at A due to the reaction force is going to add up to 0 since it's in equilibrium. And then we rearrange this to find the reaction at A, which is what we're looking for. Okay, so first we said we're drawing a primary structure. But to draw the primary structure, we're going to have to remove this reaction here. Then we're going to see that the displacement at A is no longer 0. So we're going to have a deflect shape that looks something like this. And here you see that the deflection at A can no longer be 0, which is what we've done by removing this. And we are left with a statically determinate structure. Now let's draw the real moment diagram. We're going to have the force of 10 kilonewtons acting in the middle. So the maximum moment at this point is going to be the force times by the distance, which is 0.5 L. So we have 10 times 0.5 L. Here you can see that the moment is increasing linearly across the beam. But for the column, the moment is going to be constant across the whole length of the beam. And we are also going to have the same value here. 10 times 0.5 L, since our structure is in equilibrium and this is the point where we're going to have the same moment. Now let's draw the virtual moment. We draw a unit virtual force acting at the end of the beam. So this is where we're trying to find the displacement. So you draw virtual forces, you apply virtual forces at the location where you're trying to find the displacement. And we're going to have a bending moment diagram like this, with maximum moment force of 1 times by the distance of L. And the same here. One 1.0 times L. Okay, now the moment at midspan in the middle here, we're going to need to know later, is going to be 1 times 0.5 L, because it acts across half the length. Okay, now here I've calculated the displacement at A due to the point load. And let me show you what I've used from the product integral table. These are just calculations. We have a triangle and a trapezium. So from the product integral table, we're using the triangle and the trapezium. So we're going to have BL over 6, A1 plus 2, A2. Bear in mind that the longer side on the trapezium equals the long side on the triangle, because there's also a triangle in the product integral table that looks like this, and you don't want to match this one up with our trapezium. You want to match this one up with our trapezium, so the longer length on both sides. Anyway, we also have to take in consideration 2 rectangles on a product integral table. So we're also going to have to use A times B times L. A is this length, so this moment, times B, which is this length, so this moment, times by the length L, which is the same on both sides. We've calculated it here. You may also be wondering why we've drawn the bending moment diagrams on the columns on the left side of the column. It's because the left side of the column is in tension, and you draw the bending moment diagram on the side that is under tension. Look here, you can see this side is under tension, and this side is going to be under compression. That's why we draw it on the left side. Okay, now let's draw the secondary structure. So we apply a reaction force at A in the y direction, and our deflected shape is going to look like this. And here we have displacement at A in the y direction due to the reaction force that is not equal to 0. Now, drawing the real moment diagram, due to the reaction force, our bending moment diagram is going to look like this. Basically, imagine it's been reflected in the y-axis, because usually we have the force there and the moment there, but this time it's opposite. Now, the moment is going to be the maximum moment, reaction force times by the length, and the same value of moment here, times by length. Now the virtual moment diagram, we apply a unit virtual force at A, since A is the location we're trying to find the deflection at, the displacement, and then the maximum moment here is going to be the unit virtual force times by the length L, and we're going to have the same moment here, and that's it. Now in the product integral table, we're going to have to find the formula for a triangle and another triangle, but bear in mind one of the triangle is inverted, so in the calculations we're going to have some minuses. Basically here you can see it starts, and also we take in consideration the 2 rectangles, and we get that the displacement at A due to the reaction force in the y direction is this. So we know these, and now we can apply compatibility condition. This basically tells us that the displacement at A in the y direction due to the point load, when you add it with the displacement at A due to the reaction force at A in the y direction, when you add them, they must equal 0, because the structure is in equilibrium. Now let's equate these. So we had 6.04 L cubed over EI, 6.04 L cubed over EI, plus this big one, plus, let's put it in brackets because it has a negative sign in front of it, minus 4 times RAY times by L cubed over 3EI equals 0. Let's take this to the other side. So 6.04 L cubed over EI equals 4RAY times by L cubed over 3EI. Yeah, we can simplify the EI's because it's on both sides, so we can cancel them out. Same with the L cubed. So 6.04 is 4RAY over 3. Multiply by 3, both sides. So 18.12 is 4RAY. Divide by 4. So 4.53 equals RAY. So just rearrange this. RAY is 4.53. And that is it.